Hello and welcome to today's training session on spectral response analysis, otherwise known as response spectrum analysis or seismic analysis. This webinar will be shorter than some of the others we have conducted because the spectrum analysis procedure is quite quick and easy, despite some of its concepts sounding a bit complicated. Before you can do a response spectrum analysis, you need to have specified the masses that affect the inertial properties of the structure, and you need to have done a dynamic frequency analysis. I will cover both of these steps first. You then need to set up your spectral load cases in which you nominate the response spectra to use in the analysis and the directions of the earthquake you're interested in. The response spectra are acceleration versus period curves that specify the acceleration to be used for a given vibration period and soil type. Most loading codes include 3 to 5 different response spectra that apply to different soil conditions. Once you've set up your spectral load cases, then you can run the spectral response analysis and obtain displacements, forces, moments, reactions and stresses, just like you would get from a static analysis. You can also combine them with other non-spectral load cases and use them in any of the Space Gas design modules. Note that a response spectrum analysis is linear only, and so you can't obtain buckling analysis results from a spectral load case. P-dollar effects can be allowed for manually, as I'll explain a bit later. So in this webinar I'll be discussing topics such as damping, base shear scaling, site factors, probability factors, importance factors, performance factors and mode combination methods. So let's start with a dynamic frequency analysis on the footbridge you see on the screen. The things that affect the dynamic frequency analysis are the structure itself and its stiffness, and the masses that are applied to it that affect its inertial properties. So the first type of mass is the self-mass, and we can define that via the self-weight datasheet. All we need to do in here is specify a load case number, and it doesn't matter what column we put data into here or what the magnitude of the data is. Just the fact that you've got anything in this case load case 1 means that that will become a self-mass load case. And then we also need to define any other masses as lump masses that affect the inertial properties of the model, and they could be things like superimposed dead load or other dead loads apart from self-weight, live loads, or anything else that vibrates with the structure. So in this particular model we've already got some static load cases defined. So self-weight, deck loads, roof loads, cladding, live load and then various wind loads. So you can see that these first few here, as well as being static loads, they also add to the mass on the structure. And so we can't use these directly in a dynamic frequency analysis, but we can convert them to mass load cases and then use them just like a static load case. So in order to do that we go to the loads menu, down to this tool here, the static load to mass conversion tool. Select the load cases that we want to convert to masses. We don't select self-weight because that's taken care of already, as I previously mentioned. And obviously we don't want to convert any of the wind loads to masses because they're not masses. What I'm about to say next about live load has been edited into this recorded copy of the presentation in response to comments made by some people who attended the presentation. They pointed out that live load shouldn't be used as a mass in the dynamic frequency analysis. This is correct, and we probably shouldn't have included it as a mass. If live load is present when the seismic event occurs, then it certainly affects the dynamic response of the structure. This could result in lower stresses in the structure than if it wasn't present, and so you might find that including it as a mass may be unconservative. Ultimately, it's up to you to decide. Click OK and then specify the mass load cases that they'll go into. And I'm just adding 100 to each of these static load cases just so that I can keep track of them. You can specify which load types you're converting. The conversion factor, obviously acceleration due to gravity, which you wouldn't normally change. And then this option here, which says create mass in all three directions regardless of static load direction, is normally ticked because even though a static load may just apply in one direction, when it becomes a mass, it's got inertia in generally in all three directions. So let's leave that one ticked. Click OK. Put in some titles. That are the same as the titles that they came from, just with mass on the end so we can keep track of them. You can see them displayed graphically as loads, so that's just the deck mass. Or we could look at some of the others. Looks like I misspelt that one. I'll just correct that one. Or we can turn those loads off. If you wanted to look at the lump masses that have been created by that conversion, you can go to the lump masses datasheet, and you can see here the four load cases that we created: 102, 105, 106 and 108, and you can see that the mass has been applied in all three directions. So it doesn't mean that there's three masses, it just means that there's inertia in all of those three directions. So we're now ready for the dynamic frequency analysis, and this can be done independent of a static analysis. You don't need to do any other type of analysis first. Specify the mass load cases that you want to analyze. Actually, before I do that, I just want to calculate or create a combination mass load case that combines all of those individual ones. So we want the self mass to be in it, and then if I just scroll across to find the other ones, we'll include those as well. And as you know, in the combination data sheet, you can just click on the button to the left of the combination, and it brings all of the columns to the left so that you can see exactly what's in that combination. So you can see we've got self weight or self mass, deck mass, roof mass, cladding mass, and live load as mass. And so that mass load case 200 is the one we'll use in our spectral analysis. We're just calling it total mass. So let's do the dynamic frequency analysis, and we'll just choose that load case 200. The tolerance is just the accuracy of the analysis, so if you want the frequencies to be calculated within 0.001 Hertz, then you can set that, although that setting only really applies to the wavefront and Wattcom solvers. So if you're using the Paradise solver, then that field doesn't really come into play. You can also specify an upper and lower frequency limit that just limits the frequencies to those limits if you're not interested in anything outside those. So anything greater than 1000 or less than 0.001 will just be flagged as outside of the user-defined limits. The frequency shift can be set if you're not interested in frequencies below a certain level. So for example, if you're only interested in frequencies above 2 Hertz, then you could put in a 2 and it would skip anything below that. The number of modes is normally set to something greater than 3, but 3 is the default. So let's try 50. And so that will search for the first 50 natural frequencies together with their associated mode shapes. Click OK. So at the end of the dynamic frequency analysis, you get a list of the lowest mass participation factors in each of the 3 global directions. And the mass participation factor for each direction is a reliable indicator of how well the modes you have analysed represents the overall dynamic response of the structure. So if all possible modes have been analysed, then these mass participation factors will be 100%. But because it's not practical to analyse for all modes, most loading codes allow mass participation factors greater than 90%. So in this case we're below 90%, and so we need to include a few more modes and reanalyze. So let's repeat that with 100 modes. I normally just go up in steps of 50 until you get close. But if you're way below the 90%, then you might want to go up in bigger steps. So now you can see we're okay in the X and Z directions, but not the vertical direction yet. In this case, we're not so much interested in the vertical direction because earthquakes generally vibrate in the horizontal directions, but just for the sake of completion, I'll just go and do it again with this time 150 modes. And now you can see we're well above 90% in all three directions. Once you've done a dynamic frequency analysis, you can look at the mode shapes. So each natural frequency has a mode shape attached to it. And we need to choose the load case that we've analysed. You can hold down the D key and use the mouse scroll wheel to exaggerate the vibration. And you can see in this case this is just a localized vibration in the X direction up one end. Looking over in the legend, you can see it's mode shape 1 out of 150 that has a frequency of 1.585 Hertz. A period of 0.63, which is obviously the inverse of the frequency. And then we can scroll to the next one. So it's a more generalized mode of vibration. The frequency's gone up a little bit. So these frequencies, or these modes, are all sorted in order of frequency, so starting from the lowest, working up. If you don't want to hold down the D key and use the mouse wheel, you can also use these arrows here to increase the scale if you want to. And you can change the speed by just sliding this along as well. So that's a real-time speed there. So just going through a few more of the modes, you can see they operate in different directions on different parts of the structure. And they just give you a visual reference as to what's happening to the structure at different frequencies. You can also get a report that shows a summary of the dynamic frequency analysis. If I tick the dynamic mode shapes, then you'll just get a mass of data that represents the displacements that correspond to those modes. So generally you wouldn't look at that unless you want to do something with it in another program, but in this case I'll just tick the dynamic frequencies and mass participation factors. And then you can see here we've got mass case 200, all of the modes listed, the natural frequencies in ascending order, and the mass participation factors for each of those in each direction. So the modes with the highest mass participation factor are the dominant modes. So this column that corresponds to the X direction, you can see the dominant mode for vibrations in that direction is mode 5. And slightly less dominant mode 1, and you can scroll down, and they generally tail off as you go further down, but not always. Or if you're interested in the Z direction, you've got mode 16, which is fairly dominant, also 3 and 4, 31, and so forth, and then the totals down the bottom. So once that's done, then you can start thinking about the seismic analysis. And most loading codes give you three alternatives for doing the seismic analysis. They are the equivalent static method, the dynamic response spectrum method, which is the focus of this webinar, or the dynamic time history method. So the equivalent static method is the lowest tier, which is the least efficient but which can be done by hand if absolutely necessary, whereas the two dynamic methods are obviously require a program because they're quite complex internally, even though they're simple to operate from a user point of view. If you use the equivalent static method, you must ensure that you follow the correct procedure outlined in the loading code, rather than just applying a horizontal acceleration to the structure. Applying a horizontal acceleration is widely used in the mining industry, but it is not correct and should be avoided. You can read more about the equivalent static analysis method in AS 1170.4 section 6 or the New Zealand NZS 1170.5 section 6.2 or the Indian IS 1893 part 1 section 7.6. The reason I mention those three codes is because they're the ones that we support in the spectral analysis in space gas. So the dynamic modal response spectrum method, which is the focus of this webinar, is based on the response spectra that come with the loading code and represent different soil conditions. And so when you set up your spectral load cases, you choose a spectral curve or a response spectra, a direction of the earthquake, and then you go ahead and analyze it. A time history analysis, which is also known as a transient response analysis, depends on you having some ground motion time history data for the site at which the structure is being designed. This method, although very accurate and efficient, isn't used as much as the spectral analysis method because getting that ground motion data for your site is quite difficult sometimes, or most of the time. I will demonstrate the time history method briefly at the end of the webinar though, just to show you what's involved. So let's go ahead and set up some spectral load cases, and we do that by going to the spectral loads data sheet, and we'll start with load case 301. Choose the list of modes that we want to consider. So generally speaking, you just use all the modes that you've analysed in the dynamic frequency analysis. So this is just a list 1 to 150. Choose the spectral curve. So in the case of the Australian code, you can see if I click on each one of these, you get a graph of the curve. So it's just an idealized acceleration versus period curve that corresponds in this case to strong rock. Or if I go to the next one, it's just normal rock. Next one, shallow soil, and then all the way down to very soft soil. So if I just go back to, let's say, the one that corresponds to shallow soil, and then if you look at the curve, the way these curves are used is that for a particular vibration mode, we know the period. So let's say the period is 2 seconds. Then you look up and you can see that the acceleration that corresponds to that is about 0.5 Gs. And so when we're analysing that particular mode with a period of 2 seconds, we use an acceleration of 0.5 multiplied by a factor that I'll explain a bit later. So each mode that you read across here, or the period of the mode, has a different acceleration associated with it, and that's how the spectral analysis works. So we'll click OK. The damping is included in the spectral curve, so 5% is already included in that curve, so we'll just leave that. The mass case is the load case that we've analysed previously, so number 200. And then the three columns here represent the direction of the earthquake that you're interested in. So let's say for this load case, we're interested in the X direction. And for another load case with the same data, let's set it to the Z direction. In this session, I'm not going to be covering any vertical vibrations, because most spectral analyses are predominantly just interested in the horizontal vibrations, but you can include a vertical vibration component in there too if you really want to. So rather than include vectors that have a bit of x and a bit of z, generally speaking you just have one load case for x, one for z, and then you combine those in the combination load cases later on. So let's leave it at that. Click OK. And then we'll just put in some titles. So for the first spectral load case, we'll call it earthquake in the x direction, and the other one earthquake in the z direction. The next thing we need to do is combine those two load cases into all the combinations that represent directions in between x and z. And the loading codes generally specify that the combinations need to include 100% of the data in one direction, with 30% of the data in the other direction, and all positive and negative combinations of those. So I've actually cheated and already input these because they take a little bit to set up, and I'll just show you how they work. So they're these 10 load cases down the bottom. So number 401 is all of the earthquake in the x direction with 30% in the z. The next one is 100% of x with minus 30% of z, and then we've reversed them, so 30% in the x, 100% in the z, 30% x minus 100% z. So they're the basic combinations. And then because the dynamic oscillations involve vibrations from one side to another, we also need to consider the negative of all of these spectral load cases. So that's what we've done here. So the minus earthquake in the x direction, minus the z earthquake, and then minus the combinations. So we've got the negative of 100% in x, 30% in z, and so forth all the way down. So we finish up with 10 load combinations that include the combinations of the 100% and the 30%, and then all the negative directions of those. And then if you want to combine any of those load cases with non-spectral load cases, such as normal static load cases, then you can also add those factors into the combinations. I should also mention that normal torsion is taken into account during the analysis due to the fact that we're conducting a 3D analysis. However, most earthquake codes also require allowance to be made for extra torsional effects due to the accidental eccentricity of the earthquake actions. And this isn't taken into account in the analysis. The accidental eccentricity is probably more applicable to multi-story buildings than other structure types like the one we've got here, but you should be aware that it's not done automatically. You could allow for it by moving the masses by the amount of the eccentricity, which by the way is normally around 0.1 times the planned dimension of the building, at right angles to the direction of loading. Or you could possibly do it by introducing a rotational lumped mass at the center of mass of each story of the building that represents the torsional inertia of the masses due to the eccentricity. So if you wanted to add a rotational lumped mass, you would have to create a separate mass and spectral load case for it, and then combine the results from that spectral load case with the other spectral load cases, taking into account both positive and negative rotational directions. This would involve adding some extra load combinations for the rotational spectral load case, in addition to the ones in the x and z direction. You can read more about the torsion due to accidental eccentricity in AS 1170.4 clause 6.6, or the New Zealand Code clause 5.3.2, or the Indian Code clause 7.8.2. So the next thing we can do is the spectral analysis. And because we've only got two spectral load cases, I can leave this load case field blank. Otherwise you could just go in here and select the two load cases. In this case I'll just leave it blank. And then in the next field we can choose the loading code. So you can see here we've got the Australian code, the New Zealand code and the Indian code. And in the case of the Indian code, there's different parts to it depending on the structure type that you're analyzing. We've also got a general loading code. So if you want to do a spectral analysis to a loading code that isn't one of these three, then you can tick this box, calculate manually some of the factors that the other three have got, such as these factors over here, calculate those manually and then type them into the spectral curve multiplier field over here. So starting with base shear scaling, the base shear scaling is a code-related parameter that instructs the spectral analysis to scale the results at the end so that the sum of the horizontal reactions obtained from the analysis is not less than a user-defined proportion of the total static force. And the total static force is calculated simply by multiplying the mass applied to the structure by the acceleration of the fundamental mode. So the fundamental mode is the one that has the largest translational displacement in the direction of loading. So in order to set this, it's off by default for the Australian code because the Australian code doesn't mention base shear scaling, but you can turn it on if you want to. And so if the fundamental mode is the dominant mode, then you can tick this box to have that determined automatically. Or if it's not the dominant mode, so as I explained previously, the dominant mode is the one with the highest mass participation factor, but it's not necessarily the one with the largest translational displacement, and that's the one we want to use for the base shear scaling. So if it's not the dominant mode, then you can manually find out which one has the largest displacement and specify it in here. So this is the mode that would be the fundamental mode in the x direction, or the fundamental mode in the z direction. Or if you just want to scale it using a period that you specified directly rather than getting it from one of the modes, then you can type the period in to one of these boxes in the z direction or the x direction or the z direction. You can also scale the base shear as a proportion of the total mass of the structure. So if you need more information about that, you can click the Help button. And it's pretty well explained in this text here, so you can see there's a reasonable amount written about it. Over on the right hand side we have various factors, things like the probability factor, the hazard design factor, so the location of the structure, and each location has a different hazard factor that goes up with the propensity of that location to have large earthquakes, and then the structural ductility and performance factors that depend on the structure type. So each of those four settings corresponds to a factor, so you can see the four factors there. And if we multiply those two by the structural performance factor and then divide by the ductility factor, we get the spectral curve multiplier. And the spectral curve multiplier is the amount by which the acceleration in the spectral curve that I showed earlier is multiplied during the spectral analysis. So generally speaking, you would just set these four things here, let it calculate the spectral curve multiplier, and then move on. But if you really know that you want to use your own spectral curve multiplier, then you can untick that and just type in the value that you want. Similarly, if you've got some other user-defined hazard factor, for example, you can just click the user-defined and then type it in to that box there. Over on the left-hand side, we've got the user scaling factor. Generally, you would just leave that at the default of 1, but if you wanted to take into account the extra effect of P delta effects, then you could increase that to something higher. So the loading codes generally allow you to magnify the results using a scaling factor like this to take into account P delta effects. And in the case of the Australian code, you can refer to clause 6.7.3 for that, or the New Zealand code clause 6.5.4.1. And then moving down, the sign of the results. Because the earthquake causes oscillations in both directions, the maximum values have no sign, and hence the sign of the results is indeterminate. However, usually the results are dominated by one of the mode shapes, and you could see earlier that the mode shape 5 in the x direction had a mass participation factor of 55%, so that was very dominant. And so you can select which mode shape the sign should be taken from, either by clicking here, and then I could select mode 5 for example, or I could just let it choose that automatically. So that's generally what you'd do. So during the spectral analysis, it goes through each of the modes, and in this case we've got 150 modes, and gets results for all of those, and then we need to combine them into one final set of results that represents the total response of the structure. And so the two mode combination methods that you can choose are the SRSS, or the square root of the sum of the squares, or CQC, which means complete quadratic combination. SRSS is the simplest method that works well for most situations. However, modes with closely spaced frequencies, such as within 15% of each other, are not first combined using direct summation, as most loading codes require. And so SRSS should not be used in this situation. For this reason, you should select CQC when you have modes with closely spaced frequencies. CQC is slower than SRSS, but is the recommended method for 3D analysis, especially when modes with closely spaced frequencies occur. So then we can click OK. And the spectral analysis is generally quite fast. It tells you the lowest mass participation factor, which again you've seen in the dynamic frequency analysis, and so this figure should be the same. And then we can have a look at the results. So from a spectral analysis you get results that are the same as from a static analysis. So if we go to the load case 301, you can exaggerate them by holding down the D key and using the mouse scroll wheel. So that's the earthquake in the X direction, or the earthquake in the Z direction, or you can have a look at the combinations that we created. And as well as displacements, we also get moments. They can be labeled. Shear forces, axial forces. So just like a static analysis. And then you can go ahead and use those results in any of the Space Gas design modules, just like you would using static analysis results. Looking at the reports, you can see here we can get displacements, forces, moments, reactions, and a spectral response report. I'll just limit that to maybe the reactions and the spectral response. So these are the static load cases that we haven't analysed. So if we just move down to the spectral ones, so you get reactions at the support nodes just like you would from a static analysis, and you get a total reaction. However, you need to consider that the analysis looks at the vibration of the structure and identifies the maximum values that result from it. However, the maximums at different points of the structure can occur at different times during the dynamic event. And that means that the spectral results don't represent an equilibrium state of the structure, but rather an envelope of the maximums. And that's why if you add up these individual reactions, you don't get the same as the total reaction. You also don't get a line that gives you the sum of the loads and the sum of the reactions that should be equal and opposite. So that's the earthquake in the X, then the earthquake in the Z, and then we get the combinations. And I'll just jump down to the spectral response part of the report. So this is the spectral load case 301 in the X direction. This is the input data that we specified in the datasheet and in the analysis dialog. And then further down we get a summary of the results. So for each direction we get the dominant mode, and you can see the mass participation factor for each of those directions, the base shear that's occurred, the total static force, and the mass participation factor for just the dominant mode on its own. Further down we're talking about the earthquake in the X direction, so that's this whole table applies to that, and for each mode you get the natural period, the natural frequency, and the mass participation factor. So these terms are all explained in the help system. So if you go to the help, look at the contents for spectral analysis, and then you can read about all of those in these lines here. So just going back to it again quickly, I'll just turn off the reactions and just get the spectral response report. So just going back to it, if we had turned on base shear scaling, then it would have checked that the base shear in the earthquake direction, in this load case the X direction, was not less than 100% of the total static force. And you can see here that the base shear is already 125% of the static force, and so no scaling is required. Note that the base shear scaling never scales down the results, only up if required. So looking at I'm not going to redo the analysis, but just looking at the New Zealand code, for example, the base shear scaling is normally turned on, and you can scale the base shear up to 100% of the static force or 80% of the static force, depending on the structure type. Other than that, the other changes with the New Zealand code are that you have got serviceability and ultimate limit states that you can set the factors for. And you'll notice over here some of these factors are slightly different to the Australian one, but they basically have the same effect. And looking at the Indian one, again we've got the base shear scaling, and then the factors, there's quite a lot more of them, but again they are applied in the same way as all the other codes. So while the theory and some of the terms that I've described might sound a bit complicated, you can see that the procedure from a user's point of view is quite quick and simple, and as long as you get the settings right and follow the procedure correctly, then it's quite an easy module to get results out of. I mentioned earlier that the time history method is not used often for seismic analysis because it is difficult to get the ground motion data for the site location of your structure in most cases. However, just to finish off, I'll give you a quick look at how it works using the data from the El Centro earthquake. The El Centro earthquake occurred in the Imperial Valley near the US-Mexico border in 1940 with a magnitude of 6.9. It is famous because it was the first earthquake to be recorded by a seismograph located next to a fault rupture. Its ground motion data is widely available, and so we can use it here in Space GASS. So if I go up to the data sheet, choose the transient load data sheet, and I've already input this load case with the El Centro data, but I'll just show you what I've done. So I've created the load case 310 and chosen a base acceleration problem type, which is what we've got for a seismic event. We're sticking with the mass load case 200 that's got all the masses in it that we're interested in. And then in these three columns here, we've got the data that we downloaded for the El Centro earthquake. So in the X direction, you can see here we've got the factor versus time seismogram information. So the factor in this case is basically the acceleration. You can see the values over in the table that we've just pasted in. Similarly for the Y direction and the Z direction. And we would normally also include a factor in here that's based on the parameters for the seismic event from the loading code, but in this case I'll just leave that at 1, and we'll close that. Then we can run the transient response analysis. We've only got one load case, but I'll just select it anyway. I could have left the field blank. And then down the bottom we need to specify the time range that we want to analyze over. And because the El Centro data runs for a period of 20 seconds, so the earthquake event is 20 seconds, we need to analyze for at least that time range. So let's go for 25 seconds, just so that it gives the structure a chance to settle down when the seismic event is finished. So the transient dynamic analysis takes a lot longer than the spectral analysis because it's doing a lot more calculations, but generally speaking it's only a few minutes on quite a large structure. This one will take about 3 minutes, and then after that I'll show you the animations that you can get from it and the graphs of the motion of any of the nodes showing the displacements, velocities, accelerations, etc. So just bear with me for a minute or two while this finishes. So when that's finished, we'll just turn off some of these diagrams, maybe turn the rendered view back on, and then just have a look at the animation. So we pick the load case, that's the 310, the animation speed, and then press OK. So you can see at the beginning the structure vibrates with small magnitudes and then really starts moving a lot, and then as the time goes on it gradually tapers off and then settles right down again at the end. Down at the bottom here you can see the time elapsed, and when it reaches the end it pauses for 3 seconds and then starts the animation again from time 0. And this line here represents the 25 seconds that we analysed for. You can also rotate the structure or zoom and pan while things are happening, just to see it from different angles. So that's a realistic, real-time view of how the structure would respond to that earthquake. And then if we wanted to just have a look at some points on the structure and see the actual data for the animation, we can get a graph. And here we're looking at the X displacement over time. So you can see this node only translates by about 0.5 millimeter. Let's choose a different one, maybe one up here somewhere. So this one's moving 50 millimeters at about 3 seconds into the event, and then it gradually tapers off as the structure settles down. Or if you want to look at the Y displacement, it's much less, only about 3 or 4 millimeters. Z displacements, less again, less than 2 millimeters. And then we've also got velocities. So these are the X velocities or accelerations. So you can see there it gets up to about 15 meters per second squared at the 3 second mark. So you can also get displacements, forces, moments and reactions from a transient dynamic analysis, but there's a few more steps involved to get those compared to a spectral analysis, and I won't go through those now. So I hope that's given you a fairly good overview of how the spectral analysis works. If you're still not clear on some of the aspects, then it's probably a good idea to go to the help file and just have a look at some of the information in there. In particular, if you go to the analysis section and under spectral look at the step-by-step guide, which takes you through everything in pretty clear steps with links to more detailed information, and hopefully that will answer all of your questions.